What if everything we see, the stars, the galaxies, the vast emptiness between them, is just a tiny fraction of reality? Picture this: our universe, as immense as it seems, might be nothing more than a single bubble floating in an endless cosmic foam, surrounded by countless other universes, each with its own laws of physics, its own versions of time, even its own bizarre forms of life. This isn't science fiction. It's one of the most thrilling ideas in modern cosmology: the possibility that our universe is just one hidden corner of a much grander, stranger multiverse. And today, we're diving deep into 30 of the most mind-bending theories about these hidden universes, from the wild to the scientifically plausible. Strap in, because this journey will challenge everything you thought you knew about reality. Think about the night sky, how it stretches endlessly above us, dotted with billions of stars. But what if that sky is just a veil hiding something far more extraordinary? For centuries, humans have wondered if we're alone, if there's more out there than meets the eye. Now, cutting-edge science is suggesting that the answer might be even weirder than we imagined. Some theories propose that parallel universes could be stacked like pages in a book, separated by dimensions we can't perceive. Others suggest that every decision you've ever made spawns a new universe where a different version of you walks a completely different path. The sheer scale of these ideas is enough to make your head spin, but it's also what makes them so electrifying. This isn't just about wild speculation. These theories emerge from the edges of physics, from the minds of scientists grappling with the deepest mysteries of existence. Why does our universe have such precise, fine-tuned constants that allow life to exist? Could it be pure luck, or evidence that we're just one of many universes, each with its own random set of rules? From the holographic principle to the idea of cosmic inflation, from brainworlds to quantum entanglement, we're about to explore the boldest, most provocative ideas that could rewrite our understanding of reality itself. So if you've ever stared at the stars and felt that tug of curiosity, that itch to know what's really out there, you're in the right place. Let's begin. One of the most captivating ideas in modern cosmology is the multiverse theory, the notion that our universe isn't alone but instead one of countless others, each operating under its own unique set of physical rules. Imagine a cosmic tapestry where universes bubble into existence like boiling water, each with different constants, particles, even dimensions we can't begin to comprehend. This isn't just philosophical musing, it's a framework that emerges from two of the most profound pillars of physics: quantum mechanics and inflationary cosmology. Take quantum mechanics first. At the subatomic level, particles exist in a haze of probabilities until observed, a phenomenon that led some scientists to propose that every possible outcome spawns a new universe. Picture flipping a coin. In one universe it lands heads, in another tails. Now scale that up to every decision, every random quantum fluctuation, and suddenly the idea of infinite parallel realities doesn't seem so far-fetched. Then there's cosmic inflation, the idea that our universe underwent a rapid expansion right after the Big Bang. Some versions of this theory suggest inflation never truly stops. It just keeps happening in distant regions, creating pocket universes endlessly. Think of it like a loaf of raisin bread baking in an oven, where each raisin is a separate universe forever drifting apart, some with entirely different textures or ingredients. Proponents like physicist Max Tegmark have taken this even further, classifying possible multiverses into 4 levels, from the simplest regions of space so distant they're beyond our observable horizon, to the most radical, where mathematical structures themselves define reality. The implications are staggering. If true, somewhere out there, a universe might exist where gravity is repulsive, time runs backward, or life evolved in ways we can't even imagine. And here's the twist: we may never be able to prove it directly because these other universes could be forever sealed off from our own, leaving the multiverse theory hovering tantalizingly between science and speculation. Yet for all its wildness, this idea solves some of cosmology's deepest puzzles. Why does our universe seem so finely tuned for life? If there are infinite universes with random laws, it's no surprise at least one got lucky. The multiverse doesn't just expand our sense of reality, it challenges us to rethink our place in it. Are we the rule or just a rare exception in a sea of cosmic possibilities? But how do we even begin to test something as bizarre as the multiverse? After all, if these other universes are forever beyond our reach, isn't this just cosmic speculation? Surprisingly, there are faint fingerprints, subtle clues in the fabric of our own universe that might point to something beyond. Take the cosmic microwave background, that faint afterglow of the Big Bang that fills the sky. Scientists studying this ancient light have found strange anomalies, regions where temperatures fluctuate in ways that don't quite fit our standard models. Some researchers suggest these could be collisions, scars, bruises left behind when our universe bumped against another in the early, chaotic moments of the multiverse. Picture soap bubbles floating in a sink, occasionally grazing one another. If true, these faint imprints might be our first glimpse of a neighboring cosmos. Then there's the unsettling idea of Boltzmann brains, a thought experiment that emerges directly from the concept of infinite realities. In a multiverse that's eternal and endlessly varied, random fluctuations could, in theory, assemble a fully formed, conscious brain out of nothing but chance. Not attached to a body, not born from evolution, just a lone mind spontaneously appearing in the void, complete with false memories of a life it never lived. If the multiverse is truly infinite, these Boltzmann brains should statistically outnumber ordinary, biologically evolved minds like ours, so why aren't we one of them? This paradox forces us to confront whether our perception of reality is truly reliable, or if the multiverse theory might contain some fatal flaw we haven't yet uncovered. The philosophical weight of these ideas is staggering. If every possible universe exists, then somewhere there's a version of you who became an astronaut, another who never existed at all, and yet another where the laws of physics made life impossible. It's a dizzying thought, one that redefines not just our place in the cosmos, but concepts like destiny, choice, and even meaning itself. Do our actions matter if every outcome plays out somewhere else? Or does the multiverse make existence even more precious, knowing that in most realities, life might never have gotten the chance to emerge? While the math behind these theories is rigorous, the evidence remains tantalizingly indirect. Some argue that's precisely why the multiverse is more metaphysics than physics, an idea that can't be falsified and thus falls outside the realm of science. Others counter that absence of proof isn't proof of absence, pointing to how many once controversial theories, from black holes to the Big Bang, were eventually confirmed. For now, the multiverse remains a frontier not just of space but of imagination. It challenges us to ask not just what is but what could be, and whether reality is far stranger, far richer than we ever dared to dream. Now let's step into a theory that sounds like it's straight out of a sci-fi novel, Brane Cosmology. Imagine our universe not as an isolated bubble but as a three-dimensional membrane, or brane, drifting through a higher dimensional space we can't see. Think of it like a single slice of bread floating in an enormous cosmic loaf, except this bread exists in dimensions beyond our perception. This mind-bending idea comes from string theory, which suggests that the fundamental particles of our universe might actually be tiny, vibrating strings. And if these strings exist, they could be attached to enormous brains, structures that could stretch across dimensions we can't even fathom. One of the most striking implications of Brane Cosmology is the possibility that our Big Bang wasn't a one-of-a-kind event. Instead, it might have been the result of two brains, each carrying its own universe, colliding in this higher dimensional space. Picture two sheets of paper floating in the air, gently brushing against each other. That fleeting contact could unleash enough energy to ignite an entire cosmos, creating everything we know in a single, cataclysmic instant. Physicists like Lisa Randall have explored how these collisions might not be rare at all. They could happen repeatedly, meaning our universe might just be one in an endless cycle of cosmic rebirths. What's even more fascinating is how this theory could explain some of the deepest mysteries in physics. Why is gravity so much weaker than the other fundamental forces? Brane Cosmology suggests gravity might actually be leaking out of our brain, seeping into the higher dimensions around us while the other forces remain trapped within our three-dimensional world. It's like water dripping through a sponge. Most stays put, but a little escapes into the unseen spaces, and here's where things get truly wild. If there are other brains out there drifting through this higher dimensional void, they might host universes with completely different laws of physics. Some could be barren, empty of life. Others might be teeming with civilizations we can't even begin to imagine. The eerie thought is that these parallel brains could be right beside us, separated by a dimension we'll never perceive. We might never detect them directly, but their gravitational echoes could still ripple through our reality, leaving faint traces in the fabric of space-time. Brane Cosmology doesn't just challenge our understanding of the universe, it redefines the very stage on which reality plays out. Are we living on a cosmic membrane, adrift in a sea of unseen dimensions? And if so, what happens when the next collision comes? The answers might lie not in the stars above us, but in the hidden dimensions all around us. The idea that our universe could be reborn from cosmic collisions isn't just speculation, it's a theory with real mathematical weight. In the cyclical model of Brane Cosmology, universes don't just collide once, they crash together over and over in an endless cosmic dance. Picture two enormous sheets of fabric drifting through an invisible wind, occasionally smacking into one another with enough force to spark new big bangs. Each collision resets the cosmic clock, wiping the slate clean and birthing a fresh universe with its own laws, its own stars, its own potential for life. This isn't destruction, it's recycling on the grandest scale imaginable. But how could we ever know if such a thing happened? The answer might lie in the faintest ripples in space-time itself, gravitational waves. Just as a stone tossed into a pond sends out ripples, a collision between brains would send shockwaves through the higher dimensional space around them, some of which might leak into our universe. These wouldn't be the ordinary gravitational waves we've detected from merging black holes. They'd be primordial, imprinted on the cosmos in its earliest moments, carrying echoes of the collision that birthed everything we see. Future telescopes, like the proposed Big Bang Observer or advanced versions of LISA, could one day tune into these whispers from beyond our brain. Imagine hearing the thud of another universe bumping into ours, a cosmic fingerprint hidden in the static of space-time. The implications are staggering. If we found these waves, they wouldn't just confirm Brane Cosmology. They'd tell us our universe is part of something far larger, a multiverse where collisions are as routine as sunrise. It would mean our cosmos has a history stretching back before the Big Bang, a cycle of births and rebirths we're only beginning to comprehend. And here's the twist: if brains keep colliding, then somewhere out there, another universe might be gearing up for its own Big Bang, completely unaware of ours. We could be one verse in an endless cosmic chorus, each collision a new stanza in the poem of existence. Yet for all its elegance, the cyclical model raises profound questions. If universes are endlessly reborn, do they evolve? Could some retain traces of their previous incarnations, like cosmic déjà vu? Or is each collision a total reset with no memory of what came before? The answers might rewrite not just physics but philosophy. After all, if time is cyclical, then meaning isn't a line. It's a spiral, looping back on itself in ways we're only starting to imagine. The hunt for these gravitational wave signatures is more than a scientific pursuit. It's a quest to uncover whether our universe is solo or part of an ensemble, fleeting or eternal. And with every new telescope, every refined calculation, we edge closer to hearing the heartbeat of realities beyond our own. The cosmos might not just be stranger than we think, it could be stranger than we can think, with collisions we can't see birthing universes we'll never know. But if the ripples are out there, waiting to be found, the story of existence might be far grander, far wilder than we ever dared to dream. What if the universe we experience, every galaxy, every atom, even your own thoughts, wasn't truly three-dimensional at all? Imagine reality as an illusion, like a hologram projected from a flat, two-dimensional surface at the edge of existence. This isn't a plot twist from the Matrix, it's a serious theory emerging from the intersection of black hole physics and quantum gravity, known as the holographic principle. The idea hinges on a bizarre discovery about black holes. When matter falls into one, it doesn't just vanish. According to the laws of quantum mechanics, information can't be destroyed, so somehow the details of that matter must be preserved. Scientists like Jacob Bekenstein and Leonard Susskind realized this information isn't stored in the black hole's interior, but on its surface, the event horizon, encoded in tiny, Planck-scale pixels. This revelation led to an electrifying possibility. If a black hole's interior can be described entirely by data on its boundary, could the same be true for our entire universe? The AD-S/CFT correspondence, a groundbreaking concept in string theory, suggests yes. It proposes a precise mathematical duality, a kind of cosmic dictionary that translates events in a higher dimensional space, like our 3D universe, into information on a lower dimensional boundary, a 2D surface. Picture a movie projected onto a screen. The images appear to have depth, but every detail originates from flat, encoded data. In this framework, our rich, three-dimensional reality might just be a shadow cast by interactions happening on a distant, two-dimensional plane we'll never see. The implications are staggering. If true, everything from the birth of stars to the firing of neurons in your brain could be a kind of cosmic performance with a real script written on the universe's edge. It challenges our most basic assumptions about space, matter, and even free will. After all, if reality is projected, who or what is running the projector? Critics argue the holographic principle remains speculative, lacking direct experimental proof, but supporters point to tantalizing clues like the way quantum entanglement, the eerie link between particles across vast distances, mirrors the connectivity of information on a hologram surface. Future experiments with quantum gravity or even refinements in our understanding of black holes might one day reveal whether we're living in a universe far flatter and far stranger than we ever imagined. The holographic principle doesn't just redefine reality, it asks us to consider whether the cosmos is fundamentally information, a cosmic code we're only beginning to crack. Scientists at Fermilab didn't just ponder the holographic principle, they built a machine to test it. The holometer, a high-precision laser interferometer, was designed to hunt for the faintest flickers in spacetime itself, searching for evidence that reality might be pixelated at the tiniest scales. Think of it like trying to detect the individual dots on a newspaper photograph by magnifying it until the image breaks apart into grains. The holometer's goal was even more ambitious, to find out if spacetime itself has a finite resolution, a fundamental graininess that would hint at the universe being a projection from a lower dimensional surface. How does it work? The device splits laser beams and sends them down perpendicular paths, then recombines them to measure tiny fluctuations in the light's travel time. If spacetime is smooth and continuous, the beams should stay perfectly in sync. But if reality is holographic, built from discrete, pixel-like units, there should be an inherent jitter, a quantum fuzziness in the fabric of space itself. The holometer's initial results were inconclusive, but the mere fact that such an experiment exists shows how seriously scientists take this radical idea. It's not just philosophy, it's testable physics. Meanwhile, quantum entanglement adds another layer of intrigue to the holographic puzzle. When particles become entangled, their properties link instantaneously across vast distances, defying classical notions of locality. But here's the eerie part. This spooky connection mirrors how information behaves in a hologram. On a 2D surface, every point contains data about the whole 3D image, just like how entangled particles seem to know each other's states no matter how far apart they are. Some theorists argue this isn't a coincidence. Entanglement might be the glue that binds the holographic projection, the mechanism by which lower dimensional data manifests as our seemingly solid 3D world. This leads to a staggering implication for free will. If our reality is a projection, are our choices truly ours, or just the unfolding of information etched on some distant cosmic boundary? The holographic principle doesn't necessarily spell doom for free will, but it reframes the debate. Perhaps our sense of agency emerges from the complexity of the projection, like a character in a video game making decisions based on programmed rules. Or maybe, as physicist Leonard Susskind suggests, the universe is more like a vast quantum computer, and consciousness is its way of processing the code. Either way, the holographic theory forces us to confront whether the self is as solid as it feels, or just another layer in the illusion. The holometer may not have cracked the case yet, but the hunt continues. Next-generation experiments could look for holographic noise in gravitational wave detectors or even in the behavior of ultra-cold atoms. If they find it, the implications would rewrite not just physics, but our understanding of existence itself. Are we living in a cosmic simulation, a shadow cast by data we can't see? Or is the holographic principle just a stepping stone to something even stranger? One thing's certain, the deeper we dig, the more reality seems to dissolve into questions. What if everything around you, the screen you're staring at, the air in your lungs, even the memories in your mind, wasn't real? Not in the philosophical "what is reality" sense, but in a far more unsettling way, as lines of code in an unfathomably advanced simulation, designed by beings whose technology makes our own look like stone tools. This isn't just a plot twist from the Matrix, it's a serious argument put forward by philosophers like Nick Bostrom and embraced by figures like Elon Musk. At its core, the simulation hypothesis rests on a chilling trilemma. 1. Almost all civilizations at our level go extinct before developing simulation technology. 2. If they do advance, they almost never choose to run ancestor simulations. Or 3. We're almost certainly living in one right now. Bostrom's reasoning is coldly logical. If future civilizations could simulate conscious minds even as a historical curiosity, why wouldn't they create countless iterations of their own past? And if they did, the number of simulated beings would dwarf the original biological ones, making the odds that we're the rare real ones vanishingly small. Elon Musk famously summed it up: the odds we're in base reality is 1 in billions. He argues the rapid pace of our own simulation technology, from pixelated video games to near photorealistic virtual worlds in just decades, suggests a future where indistinguishable full-dive simulations are inevitable. Imagine a universe where every advanced civilization spawns billions of simulated realities. Suddenly, the cosmic lottery doesn't look good for our authenticity. But where's the proof? Some point to glitches, oddities like the Mandela effect, where large groups share vivid false memories, like Nelson Mandela dying in prison in the 80s when he actually passed in 2013. Could these be artifacts of imperfect code, like cosmic typos in the simulation source files? Others cite quantum indeterminacy, the way particles exist in probability states until observed, almost as if the universe is optimizing processing power by only rendering what's being measured. Even the finite resolution of energy and space, Planck length and Planck time, hints at a universe built on discrete units, like pixels in a digital construct. Critics counter that these glitches have mundane explanations. Human memory is fallible. Quantum mechanics has well-tested math, and Planck scales don't prove simulation. But supporters ask a deeper question. If we were in a simulation, what better way to hide it than to make the fabric of reality feel seamless? After all, a flawless simulation wouldn't announce itself with neon signs. It would simply be, the simulation argument forces us to confront profound questions about purpose and meaning. If we're code, do our choices matter? Or is free will just an elegant subroutine? Strangely, the answer might not change much. Even in a simulation, pain and joy feel real to us. The stars inspire awe, whether they're celestial fires or data points. And if this is a simulation, well, someone went to a lot of trouble to make it convincing. Maybe that's the ultimate compliment. If we are living in a simulation, is there any way to peek behind the curtain, to find glitches in the code, or even send a message to the programmers? Some theorists argue that quantum mechanics might be our best tool for hacking the system. Take the double-slit experiment, where particles act as both waves and particles depending on whether they're observed. This bizarre behavior could be seen as an optimization trick. The simulation only renders precise details when someone's looking, saving processing power the rest of the time. If that's true, then deliberately probing quantum systems in unexpected ways might force the simulation to reveal its limits. Imagine running an experiment so complex, so unpredictable, that the system can't efficiently compute it, leading to anomalies like particles behaving in ways the underlying code can't smooth over. Another approach involves black holes, cosmic shredders, where the rules of physics break down. If information can't truly be destroyed, as quantum theory insists, then the simulation must preserve it somehow, even as matter vanishes past the event horizon. By studying how black holes scramble and theoretically eventually emit information, we might uncover artifacts of the simulation's data storage. Think of it like finding a corrupted file on a hard drive, except this file could contain clues about the programming language of reality itself. Then there's the wild card, artificial intelligence. If we create a truly conscious AI, it might start asking uncomfortable questions about its own existence and ours. A superintelligent entity could devise experiments or logic traps that expose inconsistencies in the simulation's framework. Picture an AI demanding to meet its creators, only to realize we don't know who our creators are. The irony is delicious. Our own creations might become the whistleblowers that prove we're living in someone else's code. Some have even proposed more radical methods, like trying to crash the simulation. If the universe runs on finite computational resources, flooding it with impossibly complex calculations, say by colliding particles at energies beyond natural limits, might overload the system. It's the digital equivalent of blowing a fuse, forcing a reboot, or at least generating an error message we could study. Of course, the risk is that if we're wrong, we've just wasted a lot of energy. But if we're right, the payoff would be the greatest discovery in history. The ethical implications are dizzying. If we did find proof we're in a simulation, should we try to contact the architects? Would they see us as fascinating anomalies or bugs to be patched? And what if the simulation has a purpose, like some cosmic experiment? Messing with it could be like lab rats chewing through the wires of their enclosure, with consequences we can't foresee. For now, these ideas remain speculative, closer to philosophy than physics. But as our tools grow sharper, from quantum computers to next-generation particle colliders, we might inch closer to answers. The simulation hypothesis isn't just a thought experiment, it's a challenge. If reality is a construct, then science becomes reverse engineering, and if we're lucky or clever, we might just find the back door. Picture the universe not as a single, static entity, but as something alive expanding at speeds so incomprehensible that entire new universes burst into existence like bubbles in a boiling pot of water. This is the heart of eternal inflation, a theory that reshapes our understanding of reality itself. Proposed by physicist Alan Guth in the 1980s, it suggests that the rapid expansion of space cosmic inflation didn't just happen once in the fleeting moments after the Big Bang. Instead, it's an unending process, a runaway engine of creation where certain regions of space continue inflating exponentially, while others slow down and cool off, giving rise to isolated pocket universes like our own. What makes this idea so captivating is how it tackles one of cosmology's greatest mysteries, the fine-tuning problem. Our universe seems bizarrely tailored for life, with constants like the strength of gravity or the mass of electrons set to precise values that allow stars, planets, and ultimately us to exist. The odds of this happening by chance are astronomically low unless our universe isn't the only one. Eternal inflation suggests an elegant solution. If space is endlessly spawning new bubble universes, each with random physical laws, then it's no surprise that at least one, ours, hit the cosmic jackpot. The rest might be barren, collapsing instantly, or filled with particles too unstable to form atoms. We just happen to live in the rare bubble where everything clicked. Guth's theory doesn't stop there. These bubble universes aren't just hypothetical, they're inevitable. Picture a vast, frothing ocean where each bubble is completely sealed off from the others, separated by walls of space still inflating at light speed. Some bubbles might brush against each other in the early chaos, leaving faint imprints like cosmic bruises in the microwave background radiation. Others could harbor realities where time flows backward, gravity repels, or matter behaves in ways we can't even fathom. The variety is endless, limited only by the possible combinations of physical laws. But how do we test something so grand? Indirect clues might lie in the cosmic microwave background, the afterglow of the Big Bang. If our universe collided with another bubble in its infancy, the shockwave could have left faint, ring-like patterns in this ancient light. Telescopes like the Planck satellite have hunted for these signatures, though definitive proof remains elusive. Another approach involves the nature of dark energy, the mysterious force accelerating our universe's expansion. If eternal inflation is correct, dark energy's behavior might hint at the deeper, inflationary forces at work beyond our bubble. Eternal inflation doesn't just solve the fine-tuning problem, it redefines the cosmos as a vast, bubbling multiverse where universes are born, evolve, and perhaps die, all within an unfathomably larger expanse of eternally inflating space. It's a humbling thought. Our entire universe might be just one accidental Eden in an infinite cosmic foam, a single note in a symphony of realities we'll never see. And yet, here we are, able to ponder the very forces that made us. That, in itself, is a kind of wonder. If bubble universes really are out there, drifting through an eternally inflating multiverse, then some of them must have collided, brushing against our own cosmos in its earliest, most violent moments. Picture two soap bubbles bumping in mid-air, their surfaces briefly deforming before merging or rebounding. In cosmic terms, such a collision would unleash staggering energy, sending shockwaves rippling through the newborn universe. These wouldn't be ordinary shockwaves, though they'd imprint themselves onto the fabric of spacetime itself, leaving behind telltale bruises in the cosmic microwave background, that ancient light from the dawn of time. So why haven't we spotted these bruises yet? The answer lies in the sheer scale of the problem. The cosmic microwave background is incredibly uniform, a near-perfect snapshot of the universe's infancy, but not completely uniform. Tiny fluctuations in temperature, like faint fingerprints, dot its surface. Some of these anomalies, like the infamous cold spot, have sparked speculation. Could they be scars from long ago collisions with other bubbles? The challenge is separating these hypothetical bruises from the natural noise of the early universe. It's like trying to spot a single distorted stitch in a tapestry woven from trillions of threads. Even the most advanced telescopes like Planck lack the resolution to definitively confirm or rule out these cosmic crash sites. Another complication is timing. If bubble collisions happened, they likely occurred during the first fractions of a second after the Big Bang, when our universe was smaller than an atom. Any bruises would have been stretched and diluted by 14 billion years of cosmic expansion, their signals fading into near undetectability. Add to that the possibility that most collisions would have happened outside our observable horizon, regions of space so distant their light hasn't reached us yet, and the search becomes even more daunting. But the hunt isn't hopeless. Future observatories, like the proposed CMB stage Roman 4 experiment, could scan the cosmic microwave background with unprecedented precision, hunting for the distinctive circular patterns or temperature anomalies that a bubble collision would leave behind. Other researchers suggest looking for gravitational waves from these ancient impacts, not the high-frequency waves we detect from black hole mergers today, but ultra-low frequency ripples that might still echo through the cosmos like a drumbeat from the beginning of time. The implications of finding such a bruise would be staggering. It wouldn't just confirm the existence of other universes, it would tell us something profound about our own. A collision scar could reveal the shape of the bubble we inhabit, the physics of the higher dimensional space beyond it, even the potential for other, stranger universes lurking just out of reach. Until then, these ghostly fingerprints remain hidden in the static of the cosmos, silent witnesses to a multiverse we can only glimpse in theory. But if we do find them, the story of our universe might turn out to be just one paragraph in a much larger book, one where every page is a reality unto itself. Roger Penrose, the Nobel Prize-winning physicist who helped uncover the secrets of black holes, has a theory that turns the cosmic cycle inside out. It's called Conformal Cyclic Cosmology, or CCC, and it suggests our universe isn't the first, nor will it be the last. Instead, it's one in an endless chain of cosmic eons, each beginning where the last one ended. But here's the twist: the death of one universe doesn't come from a big crunch or a collision. It comes from the quiet, inexorable evaporation of black holes. According to Penrose, when the last black hole in our universe finally vanishes, a process predicted by Stephen Hawking where these cosmic monsters slowly leak radiation until they dissolve, something extraordinary happens. The universe, now cold, dark, and empty, stretches into a state so smooth and featureless that it becomes mathematically indistinguishable from the hot, dense singularity that birthed the Big Bang. In this bizarre transformation, the end of time in one eon becomes the beginning of time in the next, like a cosmic Ouroboros eating its own tail. But how could we ever know if this happened? Penrose points to the cosmic microwave background, that ancient light from the universe's infancy. If CCC is true, some energy from the black holes of the previous eon might have imprinted itself onto our own, leaving faint, circular patterns called Hawking points, glowing hotspots where the last breaths of long-dead black holes crossed over into our new universe. These would be like cosmic postcards from a reality that existed before our own, whispers of a past we can't remember. Not everyone's convinced, though. Critics argue these so-called Hawking points could just be random fluctuations in the CMB, cosmic static masquerading as evidence. Others question whether the math behind CCC's infinite recycling truly holds up, or if it's an elegant idea stretched beyond its limits. Even Penrose admits the theory is controversial, but that's never stopped him before. After all, his work on black holes was once dismissed as mathematical fantasy until the universe proved him right. What makes CCC so captivating isn't just its audacity, it's the way it redefines eternity. Most models of the multiverse imagine parallel realities or bubbling universes. Penrose's vision is lonelier, grander. It's a universe that dies alone, only to be reborn from its own ashes again and again, with no one to witness the cycle but itself. And if he's right, the remnants of those lost eons might still be hanging in our sky, written in light we're only beginning to decode. The question isn't just whether we can find them, it's whether we're ready to accept that time itself might be circular, and that our universe is just one verse in a poem that has no beginning and no end. If time stretches backward infinitely, if our universe is just one chapter in an endless cosmic novel, then what happened in the previous chapters? Roger Penrose's conformal cyclic cosmology suggests that before our Big Bang, there was another universe, perhaps many others, each leaving faint traces in the fabric of reality. But here's the haunting question. If those lost eons harbored life, could remnants of their civilization still linger, hidden in the very light that fills our sky? Consider the cosmic microwave background, the oldest light in existence, emitted when the universe was just 380,000 years old. It's a snapshot of the cosmos in its infancy, but also a potential time capsule. If the previous eon had intelligent beings, their most enduring creations, monumental structures, vast energy projects, even something as exotic as Dyson spheres, might have left imprints when their universe met its end. Imagine a society so advanced that it encoded information in the fundamental vibrations of spacetime itself, knowing that the next universe's birth would preserve those patterns in the CMB's subtle fluctuations. These wouldn't be literal messages, but mathematical echoes, anomalies in the temperature or polarization of the microwave background that defy conventional explanation. Some researchers have speculated about the Hawking points. Penrose identified those strange, circular hotspots in the CMB. Could they be more than just relics of ancient black holes? What if they're the smeared signatures of colossal engineering projects from a universe long gone, their energy signatures stretched across eons into our own? It's a wild idea, but not impossible. After all, if a civilization mastered the ability to harness black holes or manipulate spacetime, their final acts might have rippled into the next cosmic cycle. Others propose an even stranger possibility, that the universe's constants themselves, the fine structure constant, the speed of light, might carry subtle variations encoded by prior intelligence. If the laws of physics aren't fixed across eons but slightly adjustable, a late-stage civilization might have tweaked them to leave a fingerprint for whoever came next. The CMB's minute irregularities could be a cosmic cipher, waiting for a species like ours to crack it. Of course, skepticism is warranted. The CMB's fluctuations are exquisitely well explained by random quantum noise from the Big Bang. Finding a deliberate signal in that noise would be like detecting a single whispered word in a hurricane, but the search is tantalizing. Future telescopes with ultra-precision polarization measurements might uncover patterns too ordered to be natural, or anomalies aligned in ways that suggest design rather than chaos. The philosophical weight of this idea is staggering. If true, we might not just be uncovering the physics of the universe before ours, we might be deciphering the last testament of a civilization that faced the heat death of everything and chose to leave a mark. It raises eerie questions. If we found such a message, what would it say? A warning, a blueprint for survival, or simply a desperate "we were here" etched into the bones of reality? The answers, if they exist, are written in the oldest light we can see, waiting for us to look closer. Schrödinger's cat is both dead and alive, or so the famous thought experiment goes. But what if that paradox isn't just a quirk of quantum mechanics? What if, at the moment the box is opened, reality itself splits, creating two separate universes, one where the cat survives and one where it doesn't? This is the spine-tingling premise of Hugh Everett's many worlds interpretation, a radical take on quantum physics that suggests every possible outcome of every quantum event plays out in its own branching timeline. Forget parallel universes light years away. They could be spawning right now in every atom with every choice you make. At its core, the many worlds interpretation tackles the strangest puzzle in quantum mechanics: why particles exist in a blur of probabilities until measured. Traditional quantum theory says observing a particle forces it to pick a state, like the cat being alive or dead, but Everett flipped that idea on its head. He argued the act of measurement doesn't collapse possibilities, it fulfills all of them, with each outcome hiving off into its own universe. Think of reality as a tree with infinite branches. Every time a quantum particle could spin left or right, the universe splits, and both spins happen, just in separate, newly minted realities. This isn't just about particles, though. If quantum effects underpin everything, then every decision, no matter how small, could trigger a branching point. That coffee you chose to drink this morning. In another universe, you skipped it. The job you took, the person you married, the lottery ticket you bought somewhere. Alternate versions of you took different paths, each equally real. The implications are dizzying. There might be a universe where dinosaurs never went extinct, where the Roman Empire never fell, or where you wrote this script instead of me. Critics argue the theory is untestable. How can we prove other branches exist if we're stuck in this one? But supporters point to quantum computing, where particles in superposition, existing in multiple states at once, perform calculations exponentially faster by leveraging parallel possibilities. It's as if the computer is tapping into those other branches, borrowing their outcomes to solve problems in this one. The many worlds interpretation doesn't just reshape reality, it redefines you. If every possibility happens, then your consciousness isn't a single thread but a fractal, woven through countless versions of existence. It's a humbling, exhilarating thought. Somewhere out there, in the vast tapestry of branching timelines, every what-if is real. And perhaps in some other universe, you're the one explaining this to me. If every decision spawns a new universe, then time travel might not create paradoxes, it could just create branches. The infamous grandfather paradox, where a time traveler kills their own ancestor, making their existence impossible, falls apart in the many worlds interpretation. Here's why: when the traveler steps back in time, their actions don't alter this timeline. Instead, they split off a new reality where their grandfather dies and they're never born, but the original timeline where they do exist remains untouched. It's like hopping between parallel train tracks. Derailing one doesn't stop the others. This solves the paradox but introduces a haunting question. If we could visit other branches, would we even know? Imagine jumping into a machine that promises to take you to a world where dinosaurs never went extinct. You press the button and wake up in a lush, unfamiliar landscape. But here's the catch: you wouldn't remember the moment of transition because your consciousness would seamlessly split with the new timeline. From your perspective, you've always been here. The you from the original universe might still be staring at the machine, wondering why it didn't work. Quantum mechanics throws another wrench into the idea of hopping between worlds. In the many worlds framework, branches don't just sit side by side like pages in a book, they decohere, meaning their quantum states become so different that interaction becomes impossible. Think of it like radio stations drifting out of tune. Once the frequencies separate too far, you can't switch between them. This decoherence might explain why we don't see visitors from other timelines, not because time travel is impossible, but because crossing between branches would require rewriting the fundamental laws of quantum physics. Yet some theorists speculate there might be loopholes. If parallel worlds share a quantum origin, could entangled particles act as bridges? Imagine two sides of a coin. Flip it in one universe, and its entangled counterpart in another universe might instantly land on the opposite face. While we couldn't send a person this way, information or even microscopic quantum states might, in theory, traverse the divide. Experiments in quantum teleportation already show particles influencing each other across vast distances. Could the same principle apply across realities? The many worlds interpretation doesn't just redefine time travel, it reframes it as a one-way street. You might leave your original timeline, but you'll never truly return because every action spawns new branches. It's a humbling thought. Even if we mastered the physics of jumping between worlds, we'd never find our way home. The universe isn't a fixed stage, it's a kaleidoscope, shifting with every choice, every chance, every quantum flutter. And somewhere out there, another version of you is reaching for the same impossible machine, wondering if they'll ever meet the person they used to be. What if black holes aren't cosmic dead ends, but cosmic nurseries birthing entirely new universes in their unfathomable depths? This is the radical vision of physicist Lee Smolin, who proposed that every black hole could be a gateway to a brand new reality, one where the laws of physics might be slightly tweaked, like a cosmic game of trial and error. Picture a black hole singularity not as a point of infinite destruction, but as the seed of a new Big Bang, where space, time, and even the fundamental constants reset. It's a dizzying idea. Our universe might owe its existence to a black hole in some long-forgotten parent cosmos, and inside every black hole we see today, new universes could be blooming, unseen, and unreachable. Smolin's theory, called cosmic natural selection, takes this even further. If black holes spawn universes, and those universes inherit slightly mutated versions of the laws that made them, then over generations, universes that produce more black holes would dominate the multiverse. Think of it like biological evolution. Just as organisms that reproduce prolifically outcompete others, universes fine-tuned to create countless black holes would become the cosmic norm. In this scenario, our universe's precise constants, the strength of gravity, the mass of electrons, aren't accidental. They're the result of billions of cosmic generations favoring black hole production. The eerie conclusion: we might live in a universe optimized not for life, but for making black holes. Critics argue there's no way to test whether black holes truly birth new universes after all. Anything beyond the event horizon is forever hidden from us. But Smolin counters with a provocative prediction. If his theory is correct, the laws of physics should be fine-tuned specifically to maximize black hole formation. That means stars of certain sizes should collapse into black holes more efficiently, and certain particle interactions should favor their creation. Surprisingly, some of these predictions hold up. For example, the mass of a neutron, a critical factor in how stars collapse, seems perfectly balanced to encourage black hole formation. It's as if the universe wants to make them. The implications are staggering. If true, black holes aren't just destructive monsters, they're engines of cosmic creativity, spinning off new realities where the rules are always shifting. Some daughter universes might be stillborn, collapsing instantly under unstable physics. Others could host bizarre forms of matter we can't imagine. And somewhere in this infinite lineage, our universe found the Goldilocks zone, not too hostile to life, but not so gentle that black holes become rare. Smolin's idea blurs the line between physics and philosophy. Are black holes accidental byproducts of stellar death, or the universe's way of reproducing? Is our existence just a happy side effect of a cosmos obsessed with making more of itself? We may never peer beyond an event horizon to know for sure. But the next time you look at the night sky, remember, those silent, dark voids might not be endings at all. They could be beginnings waiting. The James Webb Space Telescope has been peeling back the layers of cosmic history, revealing black holes that shouldn't exist, at least not according to our standard models. These ancient behemoths, spotted in the universe's infancy just a few 100 million years after the Big Bang, are far larger and more mature than anything their age should allow. Their existence throws a wrench into conventional theories of black hole formation. But for Lee Smolin's cosmic natural selection idea, they might be the missing piece of the puzzle. If black holes are the seeds of new universes, then the ones that form earliest when the cosmos was still young and dense would have the greatest chance to spawn offspring. Think of it like a cosmic race. The sooner a black hole forms, the more time its daughter universe has to evolve and produce black holes of its own. This could explain why JWST is finding massive black holes in the universe's toddler years. They're not anomalies, but evidence of a multiverse optimized for rapid reproduction. These primordial giants might be the universe's way of getting a head start on making more black holes, generation after generation. The math gets even more intriguing when you consider how these early black holes could form. In Smolin's framework, universes that tweak their physical constants to favor black hole formation, especially in their early stages, would dominate the multiverse over time. JWST discoveries hint that our universe might be one of those success stories, with conditions perfectly tuned to let black holes sprout like weeds in the cosmic dawn. It's as if the universe followed a recipe: take a dense, hot early environment, add slight variations in quantum fluctuations, and bake until black holes appear faster than stars. Critics argue these ancient black holes could have alternative explanations, like direct collapse scenarios where pre-stellar gas clouds bypass the star-forming stage entirely. But even these models struggle to account for the sheer size and prevalence of the black holes JWST has observed. Smolin's theory, meanwhile, predicts exactly this: a cosmos where black holes don't just form despite the early universe's conditions, but because of them. The implications are profound. If true, we might be living in a universe that's essentially a black hole factory, fine-tuned by eons of cosmic trial and error. Every supermassive black hole at the center of a galaxy, every quiet stellar mass black hole drifting in the void, could be a potential parent to a new reality with slightly different rules. And the next time JWST peers deeper into the past, it might not just be uncovering the origins of our universe, it could be glimpsing the remnants of the one that came before. Galaxies aren't just drifting apart as the universe expands. Some are moving together, pulled by something we can't see. This eerie phenomenon is called dark flow, and it's one of cosmology's most puzzling mysteries. Scientists studying hundreds of galaxy clusters noticed something bizarre. They're all streaming in the same direction at incredible speeds, as if dragged by an invisible force lurking beyond the edge of the observable universe. It's like watching leaves caught in a river current, all flowing toward some distant waterfall we can't see. What could possibly tug entire galaxy clusters with such power? One spine-tingling possibility is that the pull comes from another universe, a massive structure lurking just outside our cosmic bubble, warping space with its gravity. Picture our universe as a boat floating on an endless ocean, with currents from unseen shores nudging us off course. If true, dark flow could be the first tangible hint of a multiverse, a cosmic neighbor so close its gravity leaks into our reality. Some theories even suggest it might be a remnant of the cosmic inflation that birthed our universe, a relic of the primordial forces that shaped everything we know. But not everyone's convinced. Skeptics argue the measurements could be flawed, tiny errors in calibrating instruments or mapping the cosmic microwave background might create the illusion of motion where none exists. Others propose less exotic explanations, like vast, unseen superstructures within our own universe pulling matter toward them. Imagine a mountain range so enormous it bends rivers from thousands of miles away. Similarly, colossal clusters of dark matter might be warping space on scales we've yet to map. The debate hinges on data. Initial observations by NASA Wilkinson Microwave Anisotropy Probe and later the Planck satellite found tantalizing but inconclusive evidence. Some analyses supported dark flow, others dismissed it as statistical noise. The challenge is that whatever's causing this motion lies beyond our cosmic horizon, the farthest light we can see. By definition, we can't observe what's past that boundary, leaving us to piece together clues from its gravitational echoes. If dark flow is real, the implications are staggering. It wouldn't just prove our universe isn't alone, it would reveal that the multiverse isn't some abstract idea, but a tangible force tugging at the fabric of our reality. Future telescopes like the upcoming Euclid mission might settle the debate by mapping galaxy motions with unprecedented precision. Until then, dark flow remains a ghostly whisper from the edge of existence, hinting that the cosmos is far stranger and far more crowded than we ever imagined. Dark flow isn't the only cosmic oddity pulling our universe off balance. Lurking beyond the observable horizon lies an even deeper mystery: the Great Attractor. This colossal gravitational anomaly, situated some 250 million light-years away in the direction of the Centaurus and Norma constellations, tugs at the Milky Way and thousands of other galaxies with the force of 100 quadrillion suns. Yet we can't see what's causing it. The Great Attractor hides behind the dense stars and dust of our own galaxy's disk, veiled in a cosmic blind spot. What we do know is unsettling. It's dragging entire galaxy clusters toward it at speeds exceeding 600 kilometers per second, as if space itself is being funneled into some unseen drain. Even stranger, the Great Attractor might not be acting alone. Opposite its pull, astronomers have detected another anomaly, the dipole repeller, a vast, nearly empty region of space that seems to be pushing galaxies away. Picture a cosmic tug-of-war. On one side, the Great Attractor's invisible grip; on the other, the dipole repeller's unsettling void. Combined with dark flow, this suggests our universe isn't just expanding, it's lopsided, caught in a gravitational imbalance that defies the smooth, uniform cosmos predicted by the Big Bang. Then there's the KBC void, an enormous bubble of relative emptiness 7 times wider than the average cosmic structure, with our Milky Way sitting near its edge. Most models of the universe assume matter is evenly distributed on the largest scales, like a frothy sponge, but the KBC void flips that idea on its head. If we're drifting near the edge of a cosmic vacuum, it could explain why galaxies seem to be rushing toward the Great Attractor, like water sliding downhill toward a dense cluster of matter. The implications are staggering. If these anomalies are real, our universe might not just be asymmetrical, it could be fundamentally incomplete. The Great Attractor and dipole repeller might be local players in a much larger drama, their motions influenced by structures so immense they lie beyond our observational limits. Some theorists speculate that superclusters of galaxies, or even other universes, could be warping space-time on scales we can't yet measure. Others suggest these oddities are mere statistical flukes, cosmic illusions born from our limited viewpoint. The truth might lie in the gaps between galaxies. Upcoming sky surveys, like the Dark Energy Spectroscopic Instrument, could map millions of galaxies in unprecedented detail, revealing whether these anomalies are real or mirages. Either way, the Great Attractor and its counterparts remind us that the universe isn't just expanding, it's alive, shifting in ways we're only beginning to trace. And somewhere beyond the edge of our vision, something enormous is calling the shots. What if dark matter isn't some exotic, invisible substance but ordinary matter hiding in plain sight, just flipped sideways? This is the spine-tingling premise of mirror matter universes, a theory that suggests every particle we know could have a hidden twin in a parallel reality, identical to ours but with one crucial twist: its physics is mirrored like a cosmic reflection. In this looking glass cosmos, protons, electrons, and atoms would behave just like ours, but with left and right swapped. A mirror version of you might write with their opposite hand. Clocks would tick counterclockwise, and even the spin of subatomic particles would reverse. The most tantalizing part, these mirror particles could be the elusive dark matter that's been puzzling astronomers for decades. They'd barely interact with our world, no light, no electromagnetic force, just the faintest whisper of gravity tying the two realms together. Think of it like living in a house with invisible roommates. You only notice them when they bump the furniture. That's exactly how mirror matter could explain why galaxies rotate faster than they should. Their extra mass isn't missing. It's just hiding in a parallel universe, tugging on ours from the shadows. But how could we ever detect a universe that's literally flipped out of view? Enter right-handed neutrinos, ghostly particles that might be cosmic ambassadors between realms. Ordinary neutrinos are left-handed, spinning like a top turning counterclockwise. But if their mirror counterparts exist, they'd spin the opposite way, occasionally leaking into our universe like echoes from the other side. Experiments like the upcoming Deep Underground Neutrino experiment are hunting for these elusive right-handed neutrinos. If they find them, it wouldn't just solve the mystery of dark matter, it'd prove we're living alongside a mirror cosmos silently shaping our reality. Critics argue mirror matter is an elegant idea with too little evidence. Why haven't we seen signatures of these particles in colliders or cosmic rays? Proponents counter that mirror particles would interact so weakly they'd slip through detectors like smoke through a sieve. The only surefire way to spot them might be through gravitational anomalies, subtle warps in spacetime where mirror galaxies or stars overlap with ours. Future gravitational wave observatories could uncover these phantom overlaps, revealing hidden structures lurking just beyond our perception. The implications are staggering. If true, mirror matter would mean the universe is fundamentally symmetrical, with every star, planet, and person having a mirrored counterpart somewhere out there. But here's the haunting question. If mirror life exists, would it even recognize us? Or would we both drift forever in parallel, bound by gravity but blind to each other's light? The answer might lie in the spin of a single, elusive particle, a neutrino that refuses to follow the rules, and if we catch it, we might finally glimpse the reflection we never knew was there. Neutrinos are the universe's ultimate ghost particles, so elusive they can pass through light years of lead without a trace. But what if some of them aren't just hard to catch? What if they're slipping between realities? That's the tantalizing possibility raised by neutrino anomalies, strange discrepancies in experiments that suggest these particles might be breaking the rules we thought governed them. Take the sterile neutrino, a hypothetical fourth flavor of neutrino that doesn't interact with matter at all, not through gravity, not through the weak force, nothing. It's as if these particles are dancing just outside our universe's reach, detectable only by the gaps they leave behind in our data. The mystery began with unexpected results from neutrino oscillation experiments, where researchers watched one type of neutrino transform into another. The math said there should be three flavors: electron, muon, and tau. But the data kept showing extra flickers, like shadows moving behind a curtain. These anomalies could be explained if sterile neutrinos exist, oscillating in and out of our dimension like cosmic whispers. Some theorists suggest these phantom particles might be the missing link to mirror matter, acting as messengers between our universe and its hidden twin. Imagine a game of telephone played across dimensions where sterile neutrinos carry faint signals between realities, leaving only the faintest imprint in our detectors. Enter DUNE, the Deep Underground Neutrino Experiment, a massive project aiming to shoot neutrinos 800 miles through Earth's crust from Fermilab to South Dakota. This isn't just about measuring known neutrinos, it's about hunting for the impossible. If sterile neutrinos exist, DUNE ultra-precise detectors might catch their echoes in the patterns of ordinary neutrino oscillations. Even more intriguing, if mirror matter is real, DUNE could spot anomalies in how neutrinos interact or fail to interact with ordinary matter. Picture a window rattling from a wind you can't feel. Similarly, these experiments might detect the gravitational tug or quantum whispers of particles from a parallel cosmos. Critics argue these anomalies could be experimental errors or gaps in our understanding of conventional neutrino physics. After all, neutrinos are notoriously fickle, and tiny uncertainties in their behavior can look like revolutionary discoveries. But if DUNE or other next-gen experiments like Hyper-Kamiok and find irrefutable proof of sterile neutrinos, it wouldn't just solve a particle physics puzzle, it could crack open the door to a mirror universe. The implications would rewrite our understanding of reality, suggesting that dark matter isn't just hidden in our cosmos but woven into the fabric of another. Every sterile neutrino could be a cosmic postcard, hinting at a world identical to ours yet forever out of reach. Until then, these ghostly particles remain one of physics' most tantalizing mysteries, a shadow on the edge of discovery waiting to be seen. The Big Bang wasn't a beginning, it was a cosmic car crash. That's the explosive premise of the ekpyrotic universe theory, a radical alternative to cosmic inflation that rewrites our origin story. Picture this: our universe isn't a lone bubble inflating from nothing, but one of two four-dimensional membranes, or branes, drifting through a higher dimensional space called the bulk. These branes aren't static, they're dynamic, elastic sheets oscillating like drumheads in the fifth dimension until bang, they smash together with enough force to birth everything we know. The energy of that collision didn't just create matter and light, it sparked time itself, resetting the cosmic clock to what we now call the Big Bang. This theory flips inflation on its head. Instead of a rapid expansion from a singularity, the ekpyrotic model suggests our universe emerged from a cyclical process, like a phoenix reborn from the ashes of a previous cosmic cycle. The name even hints at this. Ekpyrosis comes from the ancient Greek for conflagration, a nod to the Stoic belief in periodic world destruction and renewal. But unlike inflation's sudden, exponential growth spurt, the ekpyrotic universe predicts a slower, smoother start, with matter and energy distributed far more evenly from the outset. Here's where the evidence gets fascinating. Inflationary theory predicts a specific fingerprint in the cosmos: primordial gravitational waves, ripples in space-time from the universe's violent infancy. These waves should leave a distinct swirl pattern in the cosmic microwave background, the afterglow of the Big Bang. Yet despite years of searching, including by telescopes like BICEP and Planck, these telltale swirls remain conspicuously absent. The ekpyrotic model, however, doesn't predict these waves. In this scenario, the collision of branes would produce a gentler, more ordered universe, one without the chaotic quantum fluctuations that inflation demands. It's as if the cosmos is handing us a clue. Maybe the Big Bang wasn't a singular explosion, but the echo of something far grander. Critics argue the ekpyrotic model has its own hurdles. For one, getting branes to collide just right to produce our universe requires impossibly fine-tuned initial conditions, like balancing two needles on a thread across a canyon. Others point out that while the lack of gravitational waves is intriguing, it's not definitive proof. They might simply be too faint for current telescopes to detect. Still, the theory's elegance lies in its cyclical nature. If branes can collide once, they can collide again, suggesting our universe might be one chapter in an endless saga of cosmic collisions and rebirths. The implications are staggering. If the ekpyrotic universe is correct, then our cosmos isn't a one-time event. It's a phase in an eternal dance of higher dimensional membranes. Somewhere out there in the bulk, another brane might be drifting toward us, destined to collide and spark the next universe. And when it does, the cycle will begin anew, with no memory of the worlds that came before. The silence of those missing gravitational waves might be more than just an absence. It could be a whisper from the fifth dimension, hinting that our origins are stranger and far more beautiful than we ever imagined. If higher dimensions exist beyond our brain, could beings there watch our universe's collisions like spectators at a concert, feeling the vibrations but never seeing the show? Imagine floating in a vast, unseen space where our entire cosmos is just one vibrating sheet among many, each collision sending shockwaves rippling through the bulk like a drumbeat. To these hypothetical higher dimensional observers, the birth of our universe might not have been a silent event. It could have been a thunderous thud, a cosmic cymbal crash echoing across dimensions. Every time branes collide, every time new universes ignite, the sound would resonate through the higher dimensional void as a symphony of creation. These beings wouldn't perceive stars or galaxies as we do. Instead, they might see our brain as a shifting, warping surface, its disturbances tracing patterns like ripples on a pond. Just as we can map the vibrations of a drumhead to reconstruct its shape, higher dimensional physicists could, in theory, decode the gravitational waves from our collisions to piece together our universe's structure without ever stepping inside it. To them, the merger of two black holes in our brain might look like a tiny knot tightening and releasing on a fabric, sending barely perceptible tremors through the bulk. Stranger still, if these beings exist, they might not even recognize our three-dimensional world as real in the way we understand it. A 4- or 5-dimensional creature could move through our brain like a hand passing through smoke, interacting with our matter only through gravity, the sole force thought to leak between dimensions. Their technology, if they have any, could manipulate space-time in ways that would seem like magic to us, bending our brain like a sheet of paper or plucking strings of energy we can't perceive. But here's the unsettling twist. If higher dimensional observers are out there, they might not care about us at all. Our universe could be just one insignificant vibration in an endless cosmic chorus, a single note in a song too vast for us to hear. Or worse, what if our collisions are merely side effects of their experiments? A civilization capable of navigating the bulk might view brain dynamics as a playground, tweaking conditions to study the universes that result. The Big Bang could have been someone else's lab accident. The idea isn't just science fiction. Physicists like Lisa Randall have seriously explored how higher dimensional gravity could explain mysteries like dark matter. If even a fraction of these theories hold water, the true nature of reality might be more layered, more alien than we ever dared imagine. So the next time you look up at the night sky, remember, something might be looking back not from the stars but from a dimension we can't even name. And if they are, they're listening to the universe's heartbeat in a way we never will. Time crystals sound like something ripped from a science fiction novel, matter that moves in an endless loop without energy, defying the laws of physics as we know them. But this isn't fantasy. It's a real Nobel Prize-winning idea proposed by physicist Frank Wilczek, and it might hold the key to understanding universes where time doesn't behave the way we expect. Imagine a snowflake that never melts, a pendulum that swings forever without being pushed. That's the essence of a time crystal, a structure that repeats not in space like ordinary crystals, but in time, oscillating perpetually in a dance that never winds down. Wilczek's bold hypothesis emerged from a simple question: could matter exist in its lowest energy state and still exhibit motion? Classical physics says no, without energy, things stay still. But quantum mechanics flips this intuition on its head. In the quantum realm, even at absolute zero, particles jitter with unavoidable fluctuations. Time crystals harness this quantum restlessness, arranging atoms into patterns that cycle predictably, like a clock that ticks with no batteries. The astonishing part, these aren't just theoretical curiosities. In 2016, researchers created the first time crystals in labs using chains of ytterbium ions and diamonds riddled with flaws, proving Wilczek's idea was more than just elegant math. Now here's where it gets cosmic. If time crystals can exist in a lab, could they also form naturally in the extreme conditions of the early universe? Some theorists suggest these structures might have emerged in the searing chaos of the Big Bang, seeding pockets of reality where time behaves bizarrely, looping back on itself, flowing in multiple directions, or even standing still. Picture a universe with no arrow of time, where cause and effect aren't linear but tangled in an infinite braid. In such a place, the future could influence the past, and entropy might run backward in regions where time crystals dominate. But why would this matter for hidden universes? Time crystals could act as cosmic architects, sculpting the fabric of spacetime in ways that birth entirely new realms. In a multiverse where physical laws vary, some universes might owe their existence to these eternal oscillations, their timelines knotted into structures far stranger than our own. Imagine a bubble universe where time loops every trillion years, resetting like a broken record, or a domain where multiple temporal dimensions intertwine, allowing beings to move through time as freely as we move through space. Critics argue that time crystals, for all their novelty, might be too fragile to shape entire universes. After all, lab-made versions are tiny and delicate, easily disrupted by external noise. But supporters counter that the early cosmos was a very different place, a cauldron of energy where quantum effects ruled supreme. In that environment, time crystals could have grown to astronomical scales, embedding their rhythms into the newborn universe like a heartbeat. The implications are staggering. If time crystals exist out there, they might not just redefine time, they could rewrite the story of creation itself. Our linear, forward-marching universe might be the exception, not the rule. And somewhere in the vastness of the multiverse, other realities could be pulsing to a rhythm we can't hear, their clocks ticking sideways, backward, or not at all. Wilczek's crystalline whispers might be the first hint that time isn't what we think, and that the cosmos is far more restless, far more alive than we ever imagined. Time crystals don't just rewrite the rules of time, they shatter one of physics' most sacred laws, the impossibility of perpetual motion. For centuries, scientists dismissed perpetual motion machines as fantasies, bound by the ironclad laws of thermodynamics. Energy can't be created from nothing, and every system loses heat over time. But time crystals laugh in the face of this dogma. They don't produce energy, they sidestep entropy entirely, moving in perfect, unchanging loops without ever winding down. Imagine a windmill that spins forever without wind, or a battery that never dies. That's the eerie magic of time crystals, and it raises a tantalizing question. If we can engineer them in labs, could nature have already sculpted them on cosmic scales? Alien civilizations, if they exist, might have harnessed this phenomenon millennia ago. Picture a society that stumbled upon naturally occurring time crystals deep inside neutron stars or the turbulent plasma of quasars, environments so extreme they warp the fabric of reality itself. These beings could have built quantum engines powered not by fuel, but by the relentless, entropy-defying rhythm of time crystals. Their cities might glow with undying light, their machines running for eons without maintenance, their entire infrastructure humming along on the endless pulse of these temporal oddities. It's a civilization where the concept of running out of power doesn't exist because their energy source isn't bound by decay, it's woven into the very structure of time. But how would such a society even function? For starters, their technology would look nothing like ours. Instead of combustion engines or solar panels, they might rely on intricate lattices of time crystal arrays, each one tuned to resonate with quantum fluctuations we can't even measure. Communication could happen instantaneously across galactic distances, not through clumsy radio waves but through entangled time crystals, their synchronized oscillations bypassing the speed of light. Even their concept of waste would be alien to us. Why bother recycling when your energy loops are infinite? The implications ripple further. If time crystals exist in nature, they might be hiding in plain sight, masquerading as cosmic anomalies. Pulsars, those spinning neutron stars that beam radiation like lighthouses, could be colossal time crystals. Their precise ticks not just a product of rotation but of quantum coherent loops embedded in their cores. Even dark matter, the mysterious substance pulling galaxies apart, might have a time crystal component, its particles oscillating in perpetual sync across the void. Critics, of course, argue that time crystals don't violate thermodynamics, they just dance around it. The energy powering their motion isn't created, it's locked in a quantum cheat code, a zero-sum game where nothing is added or lost. But supporters counter that the distinction hardly matters to a civilization that's cracked the code. To them, perpetual motion isn't a myth, it's the foundation of their reality. Here's the haunting thought: if such civilizations exist, we might never recognize them. Their signatures wouldn't be radio bursts or Dyson spheres, but subtle, rhythmic distortions in spacetime itself, patterns we're only now learning to detect. The universe could be teeming with these timeless engineers, their presence written in the quiet, inexhaustible ticking of quantum clocks we're just beginning to hear. And if we listen closely, we might catch the echo of a rhythm that never fades, a beat that outlasts stars. Black holes devour everything: light, matter, even time itself. But what if the universe has a cosmic antidote to these insatiable monsters? Enter white holes, the hypothetical twins of black holes, where instead of matter vanishing into oblivion, it erupts outward in an unstoppable explosion. Where a black hole's event horizon is a point of no return, a white hole's is a barrier nothing can cross from the outside, a cosmic fountain spewing spacetime like champagne from a bottle. Now here's the mind-bending twist. What if our entire universe wasn't born from a singularity in the traditional Big Bang, but from the cataclysmic eruption of a white hole? This idea, known as white hole cosmology, turns the story of creation inside out. Instead of a hot, dense point suddenly expanding, imagine a black hole in some other universe collapsing to its limit, then rebounding like a compressed spring into a white hole in ours. The mathematics of general relativity actually allows for this possibility, though Einstein himself dismissed white holes as unrealistic. Yet in the quantum realm, where gravity and particle physics collide, wild things can happen. Some theories suggest that when a black hole's singularity reaches maximum density, quantum effects could trigger a bounce, transforming it into a white hole. Picture a soap bubble collapsing in on itself. Just before it pops, a new bubble inflates from the wreckage. The implications ripple across cosmology. If our universe is the offspring of a white hole, it could explain why the early cosmos was so unfathomably hot and dense. It wasn't the beginning of everything, just the aftermath of a cosmic reset. This ties into the Big Bounce hypothesis, which proposes that the universe cycles through endless expansions and contractions, with each big crunch birthing a new Big Bang via a white hole's eruption. Unlike the traditional Big Bang, which starts from an inexplicable singularity, the bounce offers a cleaner transition. The energy and structure of the old universe don't vanish, they rebound. But how would we even test this? White holes, if they exist, should leave fingerprints. Some researchers speculate that gamma-ray bursts, the most energetic explosions in the universe, could be fleeting white holes ejecting matter at near light speed before snapping shut. Others suggest the cosmic microwave background might hide subtle asymmetries like echoes of a lopsided birthing event. The real smoking gun, though, would be detecting a quantum bounce signature, a specific pattern in primordial gravitational waves that defies inflation's predictions. Future observatories like the Laser Interferometer Space Antenna could hunt for these whispers from the universe's first moments. Of course, skeptics abound. White holes violate thermodynamics' second law by seemingly creating energy from nothing, and no confirmed observations exist. Yet in a quantum landscape where particles blink in and out of existence, where black holes slowly leak radiation, perhaps white holes aren't so far-fetched. They might even solve the black hole information paradox. If matter isn't truly lost inside a black hole, but stored and eventually regurgitated via a white hole, then information is preserved after all. The most haunting possibility: if white holes birth universes, then every black hole in our cosmos could be pregnant with a new reality. Our universe might be one of countless frothing bubbles in a grand cosmic foam, each birthed from the death throes of another's collapse. And somewhere beyond our event horizon, another civilization might be staring at their sky, wondering if their universe began with a bang or a bounce. The ripples in spacetime that LIGO detects from colliding black holes might carry more than just the story of cosmic crashes. They could be whispering secrets from before the Big Bang. When gravitational waves echo through the universe, they stretch and compress space itself like a drumhead vibrating after being struck. but some theorists propose these waves might contain faint, repeating patterns, subtle echoes that defy standard black hole physics. These anomalies could be evidence of a quantum bounce, remnants of a previous universe that collapsed and rebounded in the white hole eruption that birthed our own. Picture a black hole merger in our cosmos. As the event horizons stretch and merge, the gravitational waves they emit should follow a specific chirp pattern, a rapid rise in frequency and amplitude, then a smooth decay as the new black hole settles. But if spacetime has a quantum memory of its pre-Big Bang origins, the waves might exhibit a secondary signal, faint periodic echoes like a bell tolling in a cave. These echoes would arise if the post-merger black hole's event horizon isn't the perfect one-way membrane Einstein predicted, but a fuzzy quantum surface that temporarily traps gravitational waves before releasing them back into the universe. That fuzziness could be the imprint of a deeper structure, the ghostly remnants of the pre-bounce universe's spacetime, lingering like a watermark in the fabric of reality. The hunt for these echoes is already underway. In 2018, physicists analyzing LIGO data reported tentative signs of these repeating patterns in the aftermath of several black hole mergers. The statistical significance was too low to claim discovery, but the tantalizing possibility remains. Future upgrades to LIGO, like the planned Cosmic Explorer or Einstein telescope, could provide the sensitivity needed to confirm or rule out these echoes definitively. These next-generation detectors won't just listen for gravitational waves, they'll dissect them, searching for deviations from Einstein's equations that might reveal the universe's quantum skeleton. Critics argue these echoes could be artifacts of noise or subtle data processing glitches. After all, gravitational wave astronomy is still in its infancy, and teasing signals from the cosmic background is like identifying a whisper in a hurricane. But supporters counter that the echo's predicted structure, specific time delays between pulses, matches models of quantum black holes that retain a memory of their pre-Big Bang ancestry. If true, each black hole merger we observe might be a twofold event, a death in our universe and a faint resurrection of something far older. The implications would rewrite cosmology. Detecting quantum bounce echoes wouldn't just prove white hole cosmology, it would reveal our universe's genealogy, showing it was born from the collapse of another. Those echoes would be more than just sound, they'd be the cosmic equivalent of finding ancient cave paintings beneath a modern city, proof that our universe is built on ruins. And if LIGO or its successors catch them, the Big Bang might no longer be the beginning of everything, just the latest verse in an infinite poem of collapse and rebirth. What if the universe isn't governed by gravity alone, but by immense, invisible rivers of electricity coursing through space? This is the bold vision of plasma cosmology, a radical alternative to the Big Bang championed by Nobel Prize-winning physicist Hans Alfvén. Forget dark matter, invisible halos, or mysterious energy. Alfvén's universe is sculpted by plasma, the fourth state of matter, where electrons and ions dance to the tune of electromagnetic forces. Picture the cosmos not as a collection of isolated islands held together by gravity, but as a vast, interconnected web of electric currents, filaments, and cosmic circuits humming with energy. At the heart of this theory lies plasma's astonishing behavior. Unlike solids, liquids, or gases, plasma makes up over 99% of the visible universe. Stars, nebulae, even the space between galaxies buzz with this charged soup. When electrified and magnetized, plasma self-organizes into twisting ropes and colossal filaments, structures so immense they could span entire galaxies. Alfvén argued these filaments aren't just cosmic decorations, they're the scaffolding of the universe, shaping galaxies and galactic clusters without the need for dark matter. Imagine lightning frozen in time, stretched across millions of light years, its electromagnetic grasp replacing the pull of unseen mass. The evidence, Alfvén claimed, is written in the sky. Take the bizarre alignment of galaxy clusters along vast, thread-like structures called supercluster filaments. Mainstream cosmology attributes these to gravity's slow tug over billions of years, but plasma cosmology suggests they're the remnants of ancient cosmic currents, remnants of a time when electromagnetism, not gravity, called the shots. Even the spiral arms of galaxies, traditionally explained by density waves, might instead be shaped by plasma's magnetic whirlpools, like iron filings aligning around a magnet. But the most controversial claim, dark matter might be an illusion. The extra gravity needed to hold galaxies together could instead be the work of plasma's hidden electromagnetic forces. When galaxies rotate faster than expected, it's not because of invisible matter. It's because electric currents flowing through interstellar plasma create additional torque, like an unseen hand spinning a cosmic top. Critics argue this contradicts decades of gravitational observations, but plasma proponents point to lab experiments where miniature galaxies simulated in plasma chambers exhibit rotation curves eerily similar to real ones, no dark matter required. Yet plasma cosmology faces steep hurdles. The Big Bang's smoking gun, the cosmic microwave background, is neatly explained by an early hot, dense state, while plasma models struggle to replicate its precise patterns. And without dark matter, how do you explain the bullet cluster where gravity's lensing effect clearly separates from visible matter? Alfvén's answer: intergalactic plasma shocks and double layers phenomena well documented in fusion reactors but unproven at cosmic scales. The debate isn't just academic, it's a battle for the soul of cosmology. If Alfvén was right, our universe isn't a dark, gravity-dominated void but an electric tapestry, alive with currents we're only beginning to map. New telescopes like the Square Kilometre Array might settle the score, hunting for the faint radio whispers of cosmic circuits. Until then, plasma cosmology remains a defiant underdog, challenging us to reconsider whether the universe's greatest mysteries are really puzzles or just sparks waiting to be seen. Take a close look at the universe's largest structures, those immense thread-like galaxy filaments stretching hundreds of millions of light-years across the cosmos. They twist and knot like strands of a colossal spiderweb, with galaxies clustered along their lengths like beads on a string. Now, step into a plasma physics lab where researchers pass electric currents through ionized gas. What forms stunningly similar filaments, glowing tendrils of plasma that branch, spiral, and interconnect in patterns nearly identical to those galaxy-spanning threads? This eerie resemblance isn't coincidence, according to plasma cosmology. These lab-born structures, known as Birkeland currents, might hold the key to understanding the universe's skeleton. Named after Norwegian scientist Christian Birkeland, who first proposed that electric currents flow through space, these plasma filaments emerge when charged particles spiral along magnetic field lines. The result is a self-organizing dynamic structure, a cosmic transmission line capable of channeling immense energy across vast distances. On Earth, we see hints of this in the auroras, where solar wind particles ride Birkeland currents into our atmosphere, painting the sky with shimmering light. Scale this phenomenon up to galactic proportions, and you have a compelling explanation for those enormous galaxy filaments. They're not just shaped by gravity's slow pull, but by electromagnetic forces weaving the universe together like an invisible loom. Mainstream cosmology, however, remains skeptical. The Standard Model attributes these filaments to dark matter's gravitational scaffolding, a framework painstakingly built over decades of observations and simulations. According to this view, dark matter's invisible halos provided the gravitational seeds for ordinary matter to clump, eventually forming the cosmic web we see today. Plasma cosmology's alternative, that electrified currents could sculpt galaxies, challenges this deeply entrenched paradigm. Critics argue that while lab experiments show striking visual similarities, scaling plasma physics up to galactic dimensions introduces problems. For one, the universe at large is electrically neutral. The sheer scale of these proposed currents would require charge separations and energy densities that defy observational evidence. Another sticking point is the cosmic microwave background. The precise temperature fluctuations in this ancient light align neatly with gravitational models of the early universe, while plasma cosmology struggles to reproduce its detailed patterns without ad hoc adjustments. And then there's the bullet cluster, where the observed separation of visible matter and gravitational lensing strongly implies dark matter's presence, something purely electromagnetic models can't easily explain. Yet plasma proponents aren't backing down. They point to anomalies like coherent magnetic fields spanning galaxy clusters far stronger and more organized than gravity alone could produce, and the mysterious missing baryon problem, where much of the universe's ordinary matter can't be accounted for. Could this missing matter be hiding in diffuse, electrified plasma, too faint to see but powerful enough to shape cosmic structures? The debate rages on, with both sides armed with data and dismissive of the other's explanations. What's undeniable is the beauty of the parallels. Whether sculpted by gravity or electrified currents, the universe's vast filaments remind us that nature loves patterns, repeating them from the smallest lab experiment to the grandest scales of existence. The question isn't just how these structures formed, but whether we're seeing the hand of one force or many, working in concert or in competition. Until the next generation of telescopes and experiments weighs in, the cosmic web remains a tapestry with two very different sets of threads, and the choice between them could redefine everything we know about the universe's hidden architecture. The universe isn't just expanding, it's accelerating, as if some invisible force is pressing harder on the cosmic gas pedal with every passing second. Dark energy is the name we've given to this mysterious driver, but its true nature remains one of physics' greatest enigmas. What if the key to solving it lies not in the fabric of space itself, but on its edges? Enter holographic dark energy, a theory that bridges the vast emptiness of the cosmos with the mind-bending world of quantum information. Here, the vacuum of space isn't just empty, it's a buzzing, shimmering hologram, with every bit of its energy encoded on the universe's boundaries like data etched onto a cosmic hard drive. At the heart of this idea is the holographic principle, which suggests that all the information in a volume of space can be represented as encoded bits on its surface. Think of it like a movie projected onto a screen. The three-dimensional images you see are actually just shadows of data stored on the two-dimensional film. Apply this to the universe, and suddenly dark energy isn't some nebulous force filling space. It's the energy of quantum fluctuations written on the cosmic horizon, the farthest edge of what we can observe. The more the universe expands, the larger that horizon becomes, and the more bits of vacuum energy are added to the system. It's as if the universe is constantly updating its own operating system, with each new line of code driving the acceleration we observe. This ties directly into one of the biggest puzzles in cosmology. Why does dark energy's density, the amount of energy per cubic centimeter of space, seem so oddly fine-tuned? If it were slightly stronger, the universe would have torn itself apart before galaxies could form. Slightly weaker, and gravity would have crushed everything back into a singularity long ago. Holographic dark energy offers an elegant solution. The energy density isn't arbitrary, but mathematically tied to the size of the cosmic horizon. As the universe grows, the horizon's area increases, subtly adjusting the dark energy density to keep it in perfect balance. It's a self-regulating mechanism, a cosmic feedback loop written into the fabric of reality. Critics argue that the theory is still speculative, lacking the smoking gun evidence that would elevate it above other dark energy models. But supporters point to tantalizing clues. For instance, holographic dark energy predicts a specific relationship between the universe's expansion rate and the nature of dark energy, one that future telescopes like Euclid or the Vera Rubin Observatory could test. It also dovetails neatly with black hole thermodynamics, where the entropy of a black hole is proportional to its surface area, not its volume. If black holes obey holographic rules, why not the universe itself? The implications are staggering. If holographic dark energy is real, then the acceleration of the universe isn't just some random cosmic quirk. It's the inevitable consequence of information theory playing out on the grandest scale. The universe isn't merely expanding, it's computing, its boundaries humming with quantum data that shape the fate of everything within. And somewhere, written on that distant horizon, might be the answer to why we're here at all, not just as observers but as part of the code. Imagine a future where the universe stops evolving, where every possible event, every conceivable change has already happened. Stars no longer form or die. Particles cease to vibrate, even thought becomes frozen, trapped in an endless moment where time itself loses all meaning. This isn't science fiction, it's the chilling fate predicted by holographic freezing, a scenario where the cosmos reaches maximum entropy and change becomes impossible. In this state, the universe doesn't just grow cold. It becomes a static hologram where everything that ever was or ever could be is etched permanently onto the cosmic boundary, like a fossil in space. At first, this might sound like the familiar heat death, where energy disperses into a uniform, lifeless void, but holographic freezing takes it further. As the universe expands toward infinity, the amount of information it can contain approaches a finite limit, a cosmic hard drive with no room left for new data. Quantum fluctuations, the tiny vibrations that keep reality dynamic, slow to a halt. Without these fluctuations, particles can't rearrange, reactions can't occur, and time loses its arrow, not because everything stops, but because every possible configuration has already been recorded. The universe becomes a snapshot of itself, locked in an eternal present where past, present, and future blur into a single, unchanging hologram, the eerie consequence. The end of history itself. In such a state, no new stories are written, no civilizations rise or fall. Even consciousness, if it somehow persists, would be trapped in an infinite loop, replaying the same thoughts forever. It's a fate worse than oblivion, a universe that's technically still there, but devoid of any meaningful change. Philosophers call this Boltzmann's nightmare, a grotesque inversion of entropy's usual chaos. Instead of randomness, perfect order; instead of decay, perfect stasis. Yet holographic freezing might leave one final cryptic loophole. If information is preserved on the cosmic boundary, could some form of awareness persist, like a mind trapped in a frozen mirror? Theoretically, an observer at the boundary could still see the universe's entire history unfolding. But from their perspective, time wouldn't pass. Every moment would exist simultaneously, like frames of a film stacked motionless in a vault. The universe's grand narrative wouldn't vanish, it would simply become a monument to itself, a tomb of pure information waiting for no one to read it. This paradox forces us to confront a haunting question: is meaning possible without time? If the universe's final state is a frozen hologram, were all our struggles, discoveries, and dreams just temporary flickers against an inevitable stillness? Or does the sheer fact that they happen, that they're encoded forever on the edge of reality, give them a kind of immortality? The answer might lie beyond physics, in the realm of poetry. After all, even in a frozen universe, the light of dead stars still travels, and somewhere written in that light is proof that for a fleeting moment the cosmos was alive. From simulated realities where we might just be lines of code in an ultra-advanced program, to black holes that could be cosmic nurseries birthing entirely new universes inside their crushing depths, we've journeyed through some of the wildest, most mind-bending ideas in modern science. The holographic principle suggests our entire universe might be a projection from a two-dimensional surface. The multiverse theory proposes infinite realities where every possible outcome plays out. And dark flow hints that unseen forces beyond our cosmic horizon could be tugging at galaxies like puppet strings. Each of these theories stretches the limits of imagination, challenging us to rethink not just the universe but our very place within it. Yet amid all these possibilities, one question looms larger than ever. If the multiverse truly teems with life, if countless versions of us exist across infinite realities, then where is everyone? This is Fermi's paradox with a cosmic twist. Even if life is rare in our universe, the sheer scale of the multiverse should make civilizations as common as stars. So why does the cosmos feel so silent? Are we alone in a sea of possibilities, or is something or someone keeping us isolated? The answer might lie in the gaps between theories, waiting for the next great mind to uncover it. As we wrap up this journey, remember the universe's greatest mysteries aren't just puzzles for scientists. They're invitations for all of us to wonder, question, and explore. What do you think is out there? A simulation, a hologram, a multiverse humming with unseen life? Drop your wildest theories in the comments, and don't forget to like and subscribe for more deep dives into the cosmos' biggest enigmas. The conversation doesn't end here, it's just beginning. After all, in a reality this strange, the only limit is how far we dare to imagine.